And so, in fact, if we look at this little picture, we'll see that there's one little fly in the ointment. And it's a fly in the ointment that will cause us to have to add some more mechanism. So, in fact, if we think about what's happening here, that add instruction actually needs to be able to read the contents of the memory location whose address is R1 plus 0. In other words, this load instruction is going to compute the address and then go off to memory to fetch the information and stick the contents of that addressed memory location into R4. Add wants that, and you can say, well, okay, it turns out if I think about the XOR instruction, so the load is down here in the write back state. I haven't solved the problem with add yet. That's the fly in the ointment. But the XOR instruction is okay because the load is down here, and in fact, this is the cycle down here in the write-back stage that the data memory is actually coughing up the value we want. In fact, the value we want will be coming out of the WD cell mux, which means that, at least in the case of XOR, I can go ahead and bypass it back. And for some reason, I carefully bypassed it back into the A operand, even though it seems to be the B operand. So that arrow should probably be going over here somewhere. Okay. Everybody happy with that? So the XOR instruction is no problem. Our bypass pass take care of it. The trouble is that the add instruction doesn't work. And why not? Why is it? What's going wrong? Why isn't the information we have? When the load is in the ALU stage, what is actually coming out of the ALU? What do we use the ALU for when we're executing the load instruction? Yes? We're actually computing the address. So what's coming out of the ALU is not the information we want, it's the address of the information that we want. So the ALU is performing this addition, in this case of R1 plus the constant 0. And that's what's available coming out of the ALU. That is not helpful to bypass it from there. And in fact, nowhere in the machine is the information we want on some wire that we can bypass. It's still in the memory. I haven't even started the memory fetch yet. Right? We've just computed the address, and we're about to start the fetch into memory. But we haven't done it yet. So in fact, there's really no way in which the add instruction can complete its operation in the RF stage because it simply can't put its hands on the contents of R4. It's the result of the execution of the load instruction, and the load instruction simply hasn't gotten far enough along for what we want to be available to us. Does everybody understand the struggle here, right? We're looking for a value, and when we wanted the output of the ALU, that was okay, but we don't want the output of the ALU. No place to bypass it from. Okay, so here's sort of a graphic representation. What's coming out here now is the address of the memory location. You can see it's not in this 4-stage pipeline, not until the write-back stage that we actually go do that fetch. So the add instruction simply can't go anywhere. It has to stay in the RF stage until the load instruction moves forward one more stage in the pipeline. Okay, so we're going to have to introduce a notion of stalling. So if you look carefully here, you'll see that as I go from cycle I plus 2 to cycle I plus 3, the RF and IF stages are stuck. They've been stalled. We're not actually, whatever instructions were in those two, well, in this case, the add and the XOR, are sort of stuck there, and they're going to come back for a repeat appearance in cycle I plus 3. Because the add instruction, we can't get the operands yet. We have to wait until the load instruction is down here. Once we can, then we can do the bypassing, and away we go. And because the add instruction is stuck in the RF stage, the other instructions that come later in the program, okay, or earlier in the pipeline, okay, they come at earlier stages of the pipeline because they're later in the program. They just have to wait in line. They can't move forward either. They're behind us. They have to wait for their turn in the RF stage. I'm sorry, occupado, right? I mean, this stage is occupied. So the add instruction, because it's stuck, means that the RF stage is stuck at the same time. So we're going to freeze the top part of the pipeline so the instructions simply don't progress down the pipeline. And that fixes our problem. The ability to freeze the pipeline fixes the problem and allows us now in cycle I plus 3, now the data we want is coming back from memory towards the end of the cycle, and it can be bypassed, and we can get that R4 operand. There's one other small detail, which is that's fine. The add instruction has to stay here. But since the add instruction didn't move down the pipeline, but the load instruction did, in fact, we wanted the load instruction to move down the pipeline, what should we make the ALU do? Right? I mean, it's going to be sitting around saying, look, I didn't get a new customer. I didn't, the RF stage didn't send me anything. I don't really have anything to do, And so the answer is it's going to be a slacker, right? I'm going to do a no-op. So what I'm doing is when I freeze the pipeline, I start putting no-ops in for the down stages, saying, I don't have anything for you yet. Here, do nothing. So, okay, so what do we need to do? We need to go off and add some load enables to the registers here in the IF and RF stages so that, in fact, we can choose not to load them. So we have a stall signal, and in fact, when we take the inverse of the stall, so when stall is asserted or 1, not stall is 0, which means these registers, the load enables of these registers are 0, meaning they don't load. So those registers won't change their value at the end of the cycle. We also need to insert a mux here, which allows us to replace the add instruction, which is stuck here. So at the end of the cycle, we're actually going to load in a no-op. So we're going to allow ourselves to multiplex in a no-op here for subsequent stages. We have to tell the subsequent stages to do nothing. Suppose we didn't care and just let anything we want happen. Would that be okay? I mean, why are we so anal about saying, no, I have to give you a particular instruction that does nothing? Why don't we say, oh, we'll just make the signal lines be random? What would be bad about that? Yes?
You're busy fetching a specific address, so if you had to do something, you would change that?
Right. You have to be a little careful about what these guys are doing unsupervised. If you let them unsupervised, they might say, oh, I can do anything I want. How about a store into some random memory location? Right? So, the answer is that would be a bad idea. Don't leave your teenagers home at night unattended. Well, don't leave your pipeline doing anything it pleases. Really, Mom? Anything I want to do? The answer is no, dear. You can't write into main memory. Okay, so my household is strange, as you can imagine. So what we have here is a situation where we actually have to tell all the, be very explicit. And so we put in this no-op just to make sure it's not inventing something, not good to do. In this case, affecting the contents of main memory, or perhaps writing a random value into a random register. Those are all bad ideas. So we put in a no-op that makes sure that no state will be changed as a result of saying, do anything you want. Okay, so then as things move forward, we put a no-op into the ALU stage, and the load proceeds, and we're all set.